So we have here another example for tension members. This is a continuation of our topic last week. So the problem says that we have to determine the tensile design strength. So the tensile design strength, that is P Rn. Okay? And the allowable tensile strength for the allowable, that is Rn over omega. Okay? Against yielding and rupture for a W310 by 79 section shown in the figure. Okay? So we have two lines of 20 mm diameter bolt in each flange. So sabi dito, we have two lines. So isang linya yan, isang linya ng bolt. Okay? In each flange. So dalawa sa taas, dalawa sa baba. Okay? So the bolts are placed 75 mm from each other. So pagka iyan yung ano natin, section natin, meron tayong bolt that is tigdadalawang bolt that is 75 mm on center to center spacing. Ganyan. Ito yon yung 75, 75. Ito sa taas, meron din sa baba. Okay? So using A36 steel, so A36 have Fy equal to 248 MPa and Fu equal to 400 MPa. Okay? So the problem is assumed to have 3 bolts. So tatlong bolt in each line, 75 mm on center. Okay? So no bolts are staggered with respect to each other. So magkakalinya yan. So magkalinya dito, pagka dito sa taas, magkalinya dito sa baba. Okay? So meron tayong 3, tapos tatlo din dito sa baba. Okay, magkakalinya yan. So flange ng section. Okay? So ang hinahanap natin dito is the tensile design strength, yung VRN, against the yielding, so yung gross section yielding natin, and against doon sa net section fracture. And yung isa naman, yung allowable tensile strength natin against the gross yielding and against the net section fracture. So yan yung hinahanap dito sa problem. So for our solution, okay, so for our solution, let's start with the cross section against gross section yielding. Okay. So what would be our design tensile strength and what would be our allowable tensile strength? Okay? Ito yung hinahanap natin sa problem. Allowable tensile. Okay? So to solve for the design and the allowable tensile, we need to know the value . Okay, let's go back. So to solve for design and allowable tensile strength, we need to know the value of phi for the design and the value of omega for the allowable. Okay? And also, we need to determine the value of our nominal strength, that is the Rn. Okay? So what would be our phi for the gross section yielding? So what would be the value of our phi for the gross section yielding? Anong value natin ng phi dito for the gross section yielding? So we have, ano yung value natin ng phi for the gross section? Mr. Balvin.
Ma'am, 0.90.
We have 0.90. And for the omega, for the gross section, what would be our value here?
1.67, ma'am.
1.67. Okay? So we have now the value of the factors. Okay? So we need to solve the value of our nominal strength in order for us to solve for our design and allowable tensile. So what would be the equation of nominal strength against gross section yielding or yielding? What will be our equation? That is equal to Fy over Ag. Okay? Fy is given, Ag is given. So we can solve our value of Rn when we substitute value of Fy, that is 248 MPa, that is Newton mm squared, and our Ag is 10,100 mm squared. So kindly solve for our Rn value. So what will be now our value for Rn? That is equal to how much is our value for Rn?
2,480, ma'am.
2,000 ilan?
2 million, ma'am. 2,500,4,800.
In Newton. Okay, or you can convert that it in kilonewton, so that is equal to 2504.80 kilonewton. Okay, so that will be now our value for Rn. So after finding for Rn, we can now solve for the design and the allowable tensile strength against gross section yielding, since we have now the values of this Rn and then yung factor. Okay, so for the design tensile strength, that is Vrn, that is equal to phi 0.9, and the value of Rn we have 2504.8. So what would be now our design tensile strength against yielding? Ano yung value natin dito? This is equal to
2,200.
so 2,200
54.32.
32 kilonewton. Okay? And what would be now our allowable tensile strength against yielding? So for the allowable, that is Rn over omega. Our Rn is 2504.8 kilonewton over 1.67. So what would be our allowable design tensile strength against yielding? So kindly solve our value here. So kindly raise your hand if you want to give an answer. You can raise your hand if you want to give an answer para hindi kayo magsabay-sabay na magsalita.
Ma'am, ayan natin.
So we have 1499.88 kilonewton. Okay, so this will be now our answer for the design tensile strength against yielding and for our allowable tensile strength against yielding. Okay. So at the same time, we need to determine the design and allowable tensile strength against rupture. Okay. So for letter B, we have against the net section fracture or rupture. Okay. So we need to solve our design tensile strength, that is Vrn, and the allowable tensile strength, which is Rn over omega. Okay? So remember, we have different value of phi and omega dito sa net section and then doon sa gross section yielding. Okay? So what would be now our value of phi here? Miss Marquez, sorry. So for our phi, anong value natin dito?
0.75.
We have 0.75. And for our omega, what will be now our factor omega for the net section fracture? Okay, Miss Magno.
0.2, ma'am.
What? 0.2 or 2.0? We have
2.0 pala.
We have 2.0. Okay? That will be now our value for our factors for the net section. Okay? And to solve for the design and allowable tensile strength, we need to solve for the value of Rn. Okay? So for the value of Rn, for the net section, the equation of Rn is equal to Fu times Ae. Right? Fu times Ae. Okay? So Fu is given in the problem, that is equal to 400 MPa. Ae, how to solve for the Ae? So we need to solve first our Ae before we solve for our value of Rn. Okay? So the equation of Ae is equal to capital U, that is our shear log factor times the net area. Okay? So we need to find our shear log factor, and of course, we need to solve for our net area for us to determine our effective area. Okay? So for our shear log factor, for our shear log factor, that is the U. Okay, so how to determine our shear log factor? Remember, so in our introduction of the tension members, I have presented you different cases to solve for the shear log factor, right? So for W, we have two cases, case 2 and case 7. Still remember. So balikan natin ito. Case 2. This is the equation to solve for the U. Okay? So given yung L. Okay, so ano yung value ng L natin? So I have discussed in our introduction sa tension members that the value of L is the distance of the center to center, both ends ng bolt. So given sa problem, ganyan yung bolt natin, line. So we have 75 here, we have 75 here, right? So yung value natin ng L is 150 mm. Okay? So ano na yung magiging X bar natin? Ano na yung magiging X bar? Okay? So remember, pagka andito sa web, yung bolt, ang X bar natin is itong distance. Okay? Pagka andito naman sa flange, ang X bar natin is andito sa, ang location ng X bar natin, andito sa, dito. Okay? So, hindi pwede yung case 1. Diba? Since tension load is not transmitted directly. Kasi naka-eye tayo, nasa flange lang yung bolts, wala sa web. So, hindi 100% na nata-transfer yung ating tension load doon sa buong section. Okay? So, for case 2, dito kasi, alternately for W, MS, and HP, case 7 may be used. So, we need to solve the U using case 2 and then yung using case 7. Okay? And then, we need to identify yung na-solve natin sa case 2 and case 7. We need to identify what would be now our shear lag factor. Okay? So, the larger value is permitted to use. So, we need to compare yung value ng shear lag factor natin sa case 2 and case 7. Okay? So, yung mas malaking value, yun yung gagamitin nating value ng ating shear lag factor. Okay? So, inahin natin yung case 2. 1 minus x bar over L. Meron na yung value ng L natin. Ang kailangan natin yung x bar. Okay? Ano yung magiging value ng x bar natin? So, to solve for the value or to determine the value of our x bar, balik tayo doon sa ating AISC manual. Okay? So, I have given you the AISC manual. Okay, so we have here the AISC shape database natin, yung naka-Excel manual. So, saan yung X bar? Saan yung X bar natin? So, pagka tinitignan yung W310 by 79 dito sa ating section, walang value na X and Y. Walang value. So, saan natin kukunin yung X bar? Saan natin kukunin yung X bar? So, tingin tayo sa ating WT section. Okay? So, yung WT section, that is actually 1/2 of W shape. Yung WT section. So, that is the 1/2 W shape. Okay? So, pagka ito yung I mo, yung WT section, yung half ng I. So, ito na yung magiging WT section mo. Okay? So, pagka ito yung WT section mo, malalaman mo sa AISC manual, since given yung value dito, yung Y dito, yan yung magiging X bar natin sa equation natin in solving for the U. Okay? So, ang given sa problem, W310 by 79. Okay? So, i-half natin yan, W310, ano yung magiging WT natin? That is WT310 divided by 2, that is 155 by 39.5. Kaya 155 by 39.5 yung kinuha kong section ng WT. That is the half of W310 by 79. So, pagka tinitignan ninyo ito, makukuha nyo, ito yung magiging value natin ng X bar. That is 25.9. Okay? So, yan yung magiging value natin ng X bar. 25.9. So, balik tayo dito. We have, so for the case 2, shear lag factor is equal to 1 minus X bar over L. 1 minus X bar natin is 25.9 over yung L natin, that is 150 mm. Okay? So, ito yung L natin. Yan. Ito yung L natin. Okay? So, kindly solve for the value of our shear lag factor in case 2. Kindly solve this. What will be our shear lag factor here?
0.827.
So, we have 0.8827. Okay? This is not our final answer since we need to compare our capital U dito sa case 7. Okay? So, isolve muna natin yung case 7 and whichever is higher, yun yung magiging shear lag factor natin. Okay? So, sabi sa case 7, with flange connected with 3 or more. So, flange nakakonect yung ating bolt. So, kaya ito, with 3 or more, kaya ito yung kukunin natin. Okay? So, pagka web naman nakakonect yung bolt natin dito sa baba, ang U natin is 0.7. Okay, so pagka flange, we need to identify if our BF is greater than or less than 2/3 of our D, so that we can determine our shear lag factor. If our BF is greater than 2/3 of D, our shear lag factor is equal to 0.9. If our BF is less than 2/3 of D, our shear lag factor is equal to 0.85. So we need to determine the value of BF and 2/3 of D. Okay? So BF natin is given from the problem, that is equal to 254. And our D is 307. So 2/3 of D is equal to 2/3 of 307. So kindly solve the 2/3 of D. 2/3 of D. What is our value here? 2/3 of 307.
$204.67.
We have 204.67. Okay? So comparing our BF and 2/3, ano yung BF natin? BF is greater than or less than? So BF is greater than 2/3 over D. Since yung 254 mas malaki siya doon sa 204.67. So ano na yung magiging shear lag factor natin dito? Okay, greater than. Tignan natin yung greater than. So BF is greater than 2/3 of D. So our shear lag factor is equal to 0.9. Okay? So pagka less than yan, ang shear lag factor daw natin is 0.85. Okay? So comparing these two values of our shear lag factor, ano na yung magiging gagamitin nating shear lag factor in solving for our effective net area? So sabi doon sa code, we need to use the larger value of U. So larger value of U, kaya ang gagamitin natin U is yung 0.90. Okay? Kaya ang shear lag factor natin dito is 0.90. Okay? So that is for our shear lag factor. Meron pa tayong isang kukunin for us to solve the effective net area, yung ating AN or yung net area. Okay? So our net area is equal to area gross minus the summation of DE times the thickness. Okay? So ano yung magiging value ng effective hole diameter natin? Ano yung magiging effective hole diameter? Ang given dito sa ating problem is the diameter of bolt. Okay? Diameter of bolt is 20 mm. Okay? So diameter of hole is equal to 20 mm, that is the diameter of hole, plus 2 mm if our diameter is less than 24. That was discussed in the introduction of tension members. Okay? So yung diameter of hole mo is 22 mm. Ano na yung magiging effective diameter mo? So effective diameter is the hole diameter plus 2 mm. So that is the hole diameter is 22 plus 2, that is 24 mm. So yung DE mo is 24 mm. Okay? So substituting values, area gross is given, that is 10,100 mm squared, minus ilan yung butas na madadaanan pag nag-fail siya? Ilan? 4, di ba? Pag nag-fail ito, pag nag-cut yan, 2 sa taas, ang dadaanan niya, 2 sa baba pag nag-cut yan. Diba? Kaya 4 yung bolt. So 4 times the effective diameter is 24 times the thickness. Ano yung kukunin nating thickness? Ano yung kukunin nating thickness? Anyone? Ano yung kukunin nating thickness? Yung thickness ng flange, right? Since andito yung bolt. Pagka andito yung bolt, ang kukunin natin yung thickness ng web. Since yung flange is connected dito sa flange, yung bolt is connected dito sa flange, ang kukunin nating thickness is yung thickness ng flange, which is equal to 14.6. So we have 14.6. So kindly solve for the net area. This is equal to, anong value natin dito? Anong value natin dito?
It's 756.
8?
It's 7.
Ilan? 8?
It's 756, ma'am.
8756. Is this correct?
Ma'am, Han ba nga 8698.4?
So we have 8698.4. So we have 8698.4 mm squared. Okay, that is our net area. However, meron sa code natin, sabi, ang net area daw natin should not exceed the 0.85 of area gross. So yung net area natin is always lower than the 0.85 area gross. So we have to check this value. So ano yung 0.85 AG natin? 0.85 times 10,100, that is equal to 8585 mm squared. Okay? So comparing these two, ano na yung magiging AN natin? Yung net area natin. Ang na-solve nating net area is 8698.4, which is actually greater than 0.85 of AG. So we will use the value of AN that is equal to 8585 mm squared. Okay? Since yung net area dapat natin, yung maximum net area natin is 0.85 of AG. Okay? Pagka nag-exceed yung value natin ng AN dito sa 0.85 of AG, ang kukunin nating net area is the value of 0.85 AG. Pagka mas lower yung AN, ang kukunin nating value ng AN is yung computed value of net area. Okay? So yung net area natin is 8585 mm squared. Okay? So we have now the shear lag factor and then the U. So we can now solve for the AE. AE is equal to U times AN. U natin 0.9. AN natin 8585. So kindly solve for our effective net area. We have, ilan ito? 77?
26.5, ma'am.
26.5 mm squared. So ito na yung magiging AE natin. So we have now our AE, we have our FU. We can now solve for the nominal strength of our section against net section. So RN is equal to FU AE. Yung FU natin is 400 MPa times 7726.5. Ilan ito? Ano yung magiging nominal strength natin? Nominal strength, this is equal to 3096 Newton. So kindly check if my calculation is correct, or that is equal to 3090.6 kilo Newton. So tama? Tama?
Yes, ma'am.
Okay, so that will be now our value for the nominal strength. Pero hindi pala yung sagot natin. Ang hinahanap natin is the value of our design tensile strength against section fracture, and then the allowable tensile strength against fracture. So phi Sabi natin, ang phi natin, 0.75 times Rn natin, yung Rn na na-solve natin is 3090.60. So you just need to substitute values here. Masosolve na natin yung design. So ano yung value natin for design? Kindly calculate. So ano yung value natin for our design tensile strength against fracture? We have
2,117.95, ma'am. 2,317.95, ma'am.
95. 95? Is it correct? And then for our, this is for our design,
Yes, ma'am.
design tensile strength against net section fracture. And for the allowable, kindly solve for our allowable.
1545.3, ma'am.
For 1, ano?
1545.3, ma'am.
1545.3 kilonewton. So this is now our allowable tensile strength against NSF or net section fracture. So ito na yung sagot natin for the net section fracture. Okay, so we have now the design tensile strength against yielding and against fracture. We also solved the allowable tensile strength against the yielding and fracture. Okay? So, how about if the question goes like this? You just have to find, or you just have to determine the design tensile strength. What will be now your answer? So you have to find the design tensile strength. Ano yung magiging sagot natin? So from our problem, ano yung magiging sagot natin? Hindi na-identify if it is against yielding or if it is against rupture. Paano pag ganun yung question? Ano yung magiging sagot ninyo? Kasi pagka sa activity, kahit kompleto yung solution ninyo, if you don't know how to identify kung anong hinahanap doon sa question, mali pa rin. Okay? So pagka yun yung tinanong ko, ano yung magiging value natin? So remember, design sa LRFD, dalawa yung na-solve natin, di ba? Isa sa may gross section fracture and isa sa may net section fracture. Sa net section fracture, ang na-solve natin is 2317.95. And doon sa gross, we have 2254.32. 2254.32. And for the allowable, that is for the AST, dalawa din yung na-solve natin. For the gross section and then the net section. For the net section, ito yung na-solve natin, 145.3 kilonewton. And then the other one, for the gross section, we have 1499.88. So 1499.88. Okay. If my question is, you just have to determine the design tensile strength, ano yung magiging sagot natin? Ano yung magiging sagot mo, Miss Terfafag? Pagka ang tanong is, you just have to calculate the design tensile strength. Ano yung magiging sagot mo, Mr. Fafag? So, Mr. Fafag, are you there?
Hello, ma'am.
Okay. Ano yung magiging sagot natin pagka tinanong is, just have to solve for the design tensile strength. Ano yung magiging sagot natin? Anyone from the group? So what would be now our value if the problem states that we just have to determine, so we have to determine the design tensile strength. Anong magiging value natin? So, titignan natin yung sagot natin sa LRFT since we are talking about design. Okay? But the problem is dalawa yung answer natin. Against gross yielding and against net section fracture. So we just have to identify from these two which value will govern. Okay? So if you want to determine the design tensile strength, just have to compare the value computed against gross section and against net section. I-compare nyo itong dalawa. So ano yung magiging design tensile strength natin? Ano yung mag-govern na design tensile strength natin sa dalawa? Yung 2254 or yung 2317? Ano yung mag-govern? Siyempre, yung mag-govern is yung lesser value. Okay? Yung lesser value yung mag-govern. Diba? Kasi, hindi siya mag-fail sa GSF, hindi din siya mag-fail sa net section. Pagka yung higher value kasi yung nag-govern, for example, nag-govern itong higher value NSF, hindi nga siya mag-fail sa against net section, mag-fail naman siya sa gross section. Okay? So pagka lower value kasi yung kinuha natin, both gross section and net section, hindi siya mag-fail. Okay? So, PRN is equal to 2254.32. This value will govern in our design tensile strength. Okay? So for the allowable tensile strength, which of these two will govern? So for the allowable tensile strength, parehas, you have to compare the value computed against gross section and net section and get the lower section, lower value, since that will govern in our design. Okay, so for the allowable tensile strength, the value of 1499.88 kilonewton will govern. So ito na yung magiging allowable tensile strength natin. Okay, so the lower value that will govern. Okay? So pagka ang tinatanong is you have to determine the design tensile strength against gross section yielding. So your answer is 2254. Pagka ang tanong is you have to determine the allowable tensile strength against fracture. Ang sagot ninyo is 154.3 kilonewton. Okay? So, ganyan. So, pagka nagbigay ako sa activity, magbibigay ako ng A. Determine the value of. Dapat tama yung sagot ninyo. Kahit tama yung solution ninyo, pag hindi tama yung nilagay nyong sagot dito, mali pa rin yung sagot ninyo. Okay? So, you have to know how to identify what is required in the problem. Okay? So, any question for our problem 1? Any question for problem 1? Any question? Okay, kindly wait. Kindly wait lang. Wait.
Ma'am, pag-iulit man, ma'am, no, anyat yung mas dapat piliin, ag-chap-chopping nga, gamin tatay ta, di signal ko. Thank you.
Okay, come again. Sino yung nag-question? Ano yung question mo? Sino yung nag-question kanina? Pakiulit yung question kasi hindi ko narinig kanina.
Ma'am, pakiulit, ma'am, no, anya ti dapat mas piliin, ma'am.
Okay. So the design's tensile strength or the allowable tensile strength that will govern will be the lower value between the GSF and the NSF, yung gross section fracture and yung net section fracture. Okay? Kung ano yung mas mababang value, yun yung mag-govern. Okay? Para sa both gross section and net section, hindi siya mag-fail. Okay? So, pagka yung mas mataas kasi yung kinuha, hindi nga mag-fail dito sa net section fracture, mag-fail naman siya sa gross section. Okay? So, kailangan nating kunin yung mag-govern na design tensile strength is the lower value of these two. Para okay siya sa gross section, okay din siya sa net section. Okay? So, ganun. Kung ano yung mas mababang value, yun yung mag-govern for the tensile strength. Either pagka-design or allowable yung hinahanap. Okay? Any more question? Any more question? Naintindihan ba? Okay, so since walang sumasagot, I will take that as a yes. Okay, so let's move. So we have here problem number 5. Sabi sa problem number 5, we have to refer from the previous problem. Ang tanong, we have to verify if the section can carry a working dead load of 200 and a live load of 280. Okay? Verify daw natin. Okay, so from the previous problem, yung nag-govern pagka LRFD method is equal to 2254.32. That is the design tensile strength. And for the ASD, in kilonewton, 1499.88. 1499.88 kilonewton. Yan yung nag-govern pagka ASD, allowable tensile strength. Okay? So, ito yung dalawang nag-govern. The design tensile strength and the allowable tensile strength. How can we verify if our section can carry a working dead load? How can we verify? We need to compare our actual load, which is given 200 and 280, with our design or allowable. Pagka ang LRFD, we need to compare our factored actual load dito sa ating design tensile strength. And for the actual load, we need to compare this with our allowable tensile strength. Okay? So if you still remember from our code provision for LRFD, our design tensile strength should be greater than our ultimate load. Yung ultimate load, that is for our actual load. And for the ASD, our allowable tensile strength should be greater or equal to PA. That is the actual load. Okay? So, ito, na-solve na natin ito. That is 2254. And ito, we have 1499.88. So, ano yung magiging PU natin? So, we need to solve the PU. Sabi natin, pagka LRFD, ang ultimate load natin is the factored load. So, factored load, 1.2 dead load plus 1.6 live load. Kindly solve for the value of PU. Dead load natin is given 200 and live load natin is 280. So, 1.2, 200 plus 1.6 of 280. So, kindly solve for the PU. PU is equal to ultimate load.
688.
88, ma'am.
688 kilonewton. And for our actual or the allowable load, the actual load, yung actual load natin, if we are going to solve using ASD, that is the dead load plus live load. So yung PA natin is 200 plus 280. That is 480. That is our actual load. So i-compare natin ito. Itong dalawa. So we have 2254.32 kilonewton. This is greater than 688 kilonewton. And for ASD, 14999.88 is greater than PA, which is 480 kilonewton. Okay, so how can we verify? Since our design tensile strength is greater than our ultimate load, the W310 by 79 is safe to carry the given load. Okay, the same with the ASD method. Since our allowable tensile strength is greater than the actual load, our W310 by 79 is safe to carry our actual loads. Okay? So, na-verify natin na pwedeng mag-carry ng 200 dead load and live load yung W310 by 79. Okay? So, in cases that your design tensile strength exceeded your ultimate load, your section is not safe to carry the actual load. So in design, you need to revise your section. Okay? The same with the AST. If your allowable tensile design is lower than your actual load, hindi safe yung section ninyo. So you need to revise your section. Okay? So the code states that the design tensile strength is greater than the ultimate load for LRFD, and for the allowable allowable tensile strength is greater or equal to the actual load for the ASD. Okay? So safe for the LRFD and safe din pagka ASD. Okay? So do you have any question in this part?